Let us continue on this topic again, study of computing current term from the previous term. Let us take a different example this time. Compute the sine series. As before, you can pause the video and think about an alternative solution. How to solve this? X by 1 factorial minus x cube by 3 factorial plus x5 by 5 factorial. There are terms that are positive and negative. We can see that first, third, fifth terms, etc. They are positive. Second, fourth terms, even terms are appearing with a negative sign. As you might have guessed, there are several techniques to solve this. Let us discuss about one solution. Here, first we input the values of x and limit. Limit is the number of terms up to which the series is to be computed. Then here this step we convert x to a radian value. From step 5 onwards we will calculate sine x. See this term here, first term, x by 1 factorial. That is first term. Second term is x cube by 3 factorial. See how these powers are getting varied from first term to second term. X raised to 1, x cube, x5. So powers of x should be incremented with adding 2 to each term. Here when the power is 1, that same value is repeating here but as a factorial. X raised to 1 divided by 1 factorial, x cubed by 3 factorial, x raised to 5 by 5 factorial. To reflect this computation, first we will calculate factorial of j. We have not written a iterative solution for computing factorial. It is obvious when we say that we have to compute a factorial of j, this is an iterative exercise. Step 6. Once the factorial is computed, we calculate this term x raised to 1, first iteration, POW. We make use of that function. So x raised to j divided by f, x raised to j divided by f. F represents 1 factorial, POWXJ, note the value of j here. J, we start j with 1. Here. Now once the value of the first term is computed. We have to determine the size, the sign of this term. As we discussed earlier, we could see that all the odd terms are positive and all the even terms are negative. To check this, we have I. I represents term 1, term 2, term 3 like that. See here, value of I, we check whether it is odd or even. If it is even, term will be added to sum. Otherwise, term is deducted. Hence, we keep spirit of changing sign alternatively for each terms. Increment I, increment j by 2, increment I by 1, then we repeat this exercise. As before, what is special with this algorithm? This solves our issue. Sin x can be computed. But see how this solution can be improved. See the factorial computation here. In the denominator part of the sine series, each of these terms have to be computed. 1 factorial here, 3 factorial here, 5 factorial here. The given solution, we compute these factorial terms from scratch. For the first term, it is computed 1 factorial. When we reach the second term, we compute 3 factorial again. And when we move to the third term, we know that we had done an exercise to compute 3 factorial. Still, we are forced to compute it from the first. How these wasted computations can be removed? As before, now we have to ponder about how to relate each of the terms of sine series. Take the value x cubed by 3 factorial. See the value of I here, x cubed by 3 factorial. I represents the power of x now, x raised to 1, x raised to 3, x raised to 5. When I was 3, our term is x cubed by 3 factorial. X cubed, when we expand x cubed, it is x into x into x, obvious mathematics, followed by 3 factorial, 1 into 2 into 3. See the items marked with red colors. We make them adjacent now. X into x becomes x square, 2 into 3, 3 into 2. And we have taken out the other terms here. X raised to 1 by 1 factorial. Similarly, see here, I becomes 5 this term. X raised to 5 by 5 factorial. X raised to 5, x into x 5 times, 5 factorial, 1 into 2 into 3 into 4 into 5. See the items in red color. We assemble that together. We get x squared by 5 into 4, and this term x into x into x, x into x into x, x cubed by 3 factorial. Similarly, see this, the last term, I equal to 7, x is 7 by 7 factorial. This term can be written as x squared by 7 into 6 into x5 by 5 factorial. Can we see any kind of relation between these terms? See x3 by 3 factorial and x1 by 1 factorial. We have x5 by 5 factorial here. We have x3 by 3 factorial here. x7 by 7 factorial. We have x5 into 5 factorial. Let us take these terms. X squared by 3 into 2, x squared by 5 into 4, and x squared by 7 into 6 in each of these terms. Is there any way to generalize this term? See this x squared. We can see that x squared it can be computed as a constant value for a given solution. We can easily compute that. So in each of these terms, x squared will be used to generate this term. What about 3 into 2? 3 into 2. Here we have 3. This 3 and 3 into 2. I becomes 3. When I becomes 3, we multiply 3 into 2. When the value was I was 5, we multiply 5 with 4. When the value of I was 7, here we multiply 7 with 6. How to generalize this x squared by 3 into 2 portion? Value of I is 3, we get 3 into 3 minus 1. Value of I was 5, we get 5 into 5 minus 1. When the value of I was 7, here the denominator was 7 into 7 minus 1. Hence we can see that this portion can be easily generalized as x squared by I into I minus 1. Hence, we could find a generalized solution for the first part of this term computation. Now let us see this portion. x1 by 1 factorial, x3 by 3 factorial, and x5 by 5 factorial. How this term can be even generalized and related each other. See the value here. value of I is 5. When the value of I is 5, we have to compute x raised to 5 by 5 factorial. We have decomposed that this way. Value of I is 5, so the first term will be x square by 5 into 5 minus 1, 5 into 4, x square by I into I minus 1. This portion we have already seen. Take this term now, x cubed by 3 factorial. This x cubed by 3 factorial we have seen elsewhere. Watch the previous term. When the value of I was 3, we get x cubed by 3 factorial. See, when the value of I is 5, this term is generated from the previous term. Similarly, take the term here, I becomes 3. When I becomes 3, we compute x cubed by 3 factorial. First part, we know what will happen. X square by 3 into 3 minus 2. 3 minus 1, sorry, 3 minus 1. See this part, x1 by 1 factorial. This x1 by 1 factorial is in fact our first term. This is the second term. We generate second term from the first term. We generate the third term from the second term. We generate the third term from just previous term, second term. That means we can easily reconstruct the current term from previous terms. And armed with this relationship, that means each of these terms have now two portions. One term can be generated just from the value of I. Value of I indicates the power of x. This is safe now. For in each iteration, this portion will be x square by I into I minus 1. Second portion. The second portion is just the term we have computed in the earlier iteration. See how it is diagrammatically represented here for a better visualization. As we discussed, I equal to 3, we have computed this term. When the value of I became 5, to generate the third term, it is written as such, x square by 5 into 4, and we get this x3 by 3 factorial here. And this exercise continues for the current term for this x7 by 7 factorial also. We had discussed this portion. When I equal to 5, we reconstruct that term from the previous term. When I equal to 7, we get x square by 7 to 6 followed by x5 by 5 factorial, which is the earlier term. See how our problem reduces now. Each term can be computed as follows: x square by I into I minus 1 into previous term, x square by I into I minus 1 into previous term. This is the first term. This is a second term, x cube by 3 factorial. We generate the third term, x5 by 5 factorial, from the second term. Now, armed with this information, let's redesign the solution that we have done earlier. We start with our I, our x raised to I. I is 1, j is 1, initial value is, the accumulated value is 0. As usual, we input x and limit. See, x into x is given as x. Just watch this, x is equal to x into x. We get the first term as x itself, because it is x by 1 factorial, so first term is x itself. Now from step 6 onwards, we compute our sum while I is than or equal to limit. See this computation. T, this is the new term now. T into xx. Xx is nothing but x square. T into xx divided by I into I minus 1. Yes. T into xx by I into I minus 1. And this term xx by divided by I into I minus 1, this term is multiplied with the previous term. So when we iterate this, at the beginning we have the initial value t equal to x. X by 1 factorial is x, and it is the first term is given to t. Remember, we have outlined the steps earlier to arrive at this technique. We have to find an initial value which cannot be iteratively constructed, and in this case that term is nothing but x by 1 factorial that we have computed here, t equal to x. Once the first term is generated, all other terms will be generated from the previous terms. In the first iteration, we will get the previous value as x. X will be multiplied with x square by I into I minus 1. xx into I divided by I into I minus 1. This portion should be obvious to you now, because this exercise we have done earlier also. We have to compute the sign of each terms depending upon the value of I. Now let us compare how these two solutions differ. This is our solution 2 and this is a revised solution. See here this portion. In the solution 1, we tend to compute the denominator of each term from the scratch. And same thing is being done in the power calculation also. X raised to 1 is computed. Then we compute x cube from the scratch. Then we compute x raised to 5 from the scratch without capitalizing on the earlier computations. X raised to 3 is computed for the second iteration. Still, the third iteration, we repeat the power calculation again. How these two heavy computative aspects are eliminated in the revised solution. See here, x square by I into I minus 1. Here we see that x square is a constant term and it is loop invariant. Value of x into x doesn't change for a given term. Hence, this term x into x is calculated outside the loop and is kept in a different variable x. We save that many times of multiplications. Then when we compute the current term from the previous term, we could eliminate one more inner loop. This is how this technique of generating the current term from previous term can be applied wherever possible to reduce the computations and to arrive at efficient solutions.